Good morning, everyone. Thank you for attending this doctoral meeting. Today, our speaker is Faranak Karimpour, I think. And she's a second-year PhD student in here, so you probably know her already. And her talk is entitled "In Memory Computing CMOS Circuits for Computer Vision Deep Learning." And she's doing the PhD here under the supervision of Dr. Daniel García Lesta and Dr. Fernando Rafael Pardo Seco. This topic is quite far from my field of expertise, if any. So I will just let you start whenever you're ready. Thanks.
Hello, everyone. Thank you for joining today. I'm excited to share our recent research with you, focusing on in-memory computing CMOS circuits for computer vision deep learning. As I begin this presentation, I aim to outline there is the structure of my research that consists of four main parts. I will start with a brief introduction, followed by architectures and circuit. Then I will talk about simulation results before concluding our discussion. Today, I'm going to be talking about how we can give machines a sense of vision. Sighted people rely on vision every day, and they can use it for things like manipulation, navigation, recognition objects, and other things. Computer vision is an area of AI that enables system to derive information from images, videos, and other visual inputs and take actions based on that information. Computer vision has a rich history dating back to 1950s. Dating back to 1950s, from early attempt to at teaching computers visual understanding to the breakthroughs in 2010 with advent of deep learning and CNNs. Computer vision has transformed how we approach immigration tasks. The fields highlight significance from edge computing in 1970s until 1980s to the recent progress with transfer learning, specialized hardware in 2010s and beyond. Now I'm going to review how deep learning can build powerful computer vision sensors capable of solving multiple tasks that may just 15 years ago not have been possible to solve. A deep neural network, as you can see in the picture, is a artificial neural network with multiple hidden layers between input layers and output layers. Now, examples of how deep learning can transfer computer visions are facial detection, speech recognition, autonomous driving, and drug discovery. In this research, I will focus on the specific class of deep neural network that has significantly impacted image recognition and classification, convolutional neural network, or CNNs. What computers see that we as humans solve it every day, and we can also train machines to solve. Then the question is how computers can see, or how computer can process an images or a video. As you can suppose we have this picture here. Computer images are just numbers, and each of suppose in this picture we have some kind of pixels, and each of these pixels can be represented by numbers. So we can represent our image as a 2D matrix of numbers. Now let's see one example of convolution operation. To compute the convolution operation between the 5x5 image with a kernel of 3x3, we slide the kernel over the image and performing element-wise multiplication and summing them for the single output. This process continues until we generate a feature map. Let's delve into the fundamental principle differences between two computing paradigms. Von Neumann architecture is on traditional computing and in-memory computing. Von Neumann relies on frequent data movement between memory and processing units and causing high consumption energy. In contrast, IMC performs computations directly within memory cells and minimizing the data transfers and also energy consumption. The shift to IMC signifies advancement, especially in tasks like dot product computations. In the convolutional process of CNN, the inner product operation involves multiplying the feature kernel with the input image elements. If we want to describe this process inside our circuit, various strategies exist. As you can see in this schematic, we have one switch is connected to the capacitor, and we have the current source, which is the current is passing through the capacitor and switches. This approach has a strategy of charging or discharging a capacitor with a certain current, at a given time, and we can explain it also with this equation. If subsequently we'll extend this explanation into our circuit, introducing a 3x3 multiplayer. The configuration depicted here comprises a grid of MAC units in a 3x3 layout. Each unit multiplies a ratio element, I, which is the input current proportional to the corresponding weights, and T read proportional to the input values. As you can see in this schematic, we have the T as an input values and the I as an input as a current, and the I with indices T 0, 0 and T with indices 0, 0 represents the first multiplier in a 3x3 weight matrix. And the contribution of all these multipliers are accumulated in a shared capacitor, yielding the final voltage output. In this slide, we explore multiple approaches in the realm of current time multiplication for MAC operations. The focus is on 4 distinct strategies: PRSS and PSS structure, positioning switches. As you can see here, we have one single switch before the single transistor current source that we name it PRSS, and we have one single switch that is after the current source that we name it PSS structure. Single switch, that means that we have only one switch is connected to the logic, and instead of having one switch, we can also have multiple switches featuring 3 transistors in series. And also, we analyze the different voltage differences in different structure at 1.8 volts and 3.0 volts voltage domains. In this study, we examine 2 5-bit sign multiplayer, PRSS and PSS structure. Here, the PRSS structure, we design it with a focus on minimizing the error voltage and also the performance. Our circuit schematic employs 3 PMOS for both of them, PRSS and PSS structure. 3 PMOS transistors in upper branch and 3 NMOS transistors in the lower branch. Again here, before or after the single transistor current source. So the signals of the gate terminal of these transistors are connected to the sign which indicates the positive or negative weights, the P-bit line that is stored in a SRAM, and the T-read as an input value. As a fundamental principle, the PMOS transistor is turned on by applying the negative gate source voltage, and the NMOS transistor is activating by applying positive gate source voltage. So for a sign bit of 1, the PMOS transistor is activated and NMOS remains off, achieving 0 current in the lower branch and the desired current level in the upper branch. Conversely, a sign bit of 0 reverses this behavior. And then we have made one change in our design. Instead of having 3 transistors in series, we have one single transistor which is connected to the design and to the logic and controlled by it. And this change enhances our performance, significantly reduces the error voltage, although it has a lot of transistors in its logic. This crucial aspect of our system involves creating of voltage biasing using current source, single transistor current source for positive and negative bits. In addition, our design incorporates a reference current reference current mechanism to create four distinct currents, as illustrated in the schematic of bias here. This input current source is mirrored by the ratio of 1, 1/2, 1/4, and 1/8. In our analysis, key metrics are considered to evaluate the performance of our system. The capacitive equation as expressed here, we have capacitive behavior when the current and time are at the maximum values. Also, about the capacitive calculation and values were precisely chosen to ensure the transistors remain in transistor saturation based on the weight current and T-read LSBs optimized at 128 femtofarad and 288 femtofarad in one single multiplayer. As an equation of the voltage precharge that quantifies the differences between the maximum and minimum voltages, we evaluate the voltages, the optimal voltages in a voltage precharge equation to ensure the transistors remain in saturation region. For example, in 1.8 voltage, we have a voltage precharge of 0.9 volt. That indicates the initial voltage level is set to 0.9 volt before a circuit undergoes further operations. And also, we have the least significant bit of current and T-read, which are 20 nanoampere, 40 nanoampere, and 20 nanosecond, and 40 nanosecond, and 1.8 volt and 3.3 volt voltage. The designs are configured with weight bits of I with indices IJK from nearby digital memory cell, and the mathematical representation involves pulse width modulation with denoted as T-read with indexes IJK, and the products of all these multiplayers are computed as I in T-read. The voltage at the load capacitor over time is expressed in this equation that reflects the increase or decrease of the voltage based on the current. The voltage maximum here in this equation is expressed by an equation that we have the maximum values for from the positive 15 to negative 15, which is 31, and we have also the maximum value for the input. The error percentage has a specific equation that quantifies the deviation between the ideal and the simulated value. Now let's examine the effect of parasitic capacitance in the PRSS and PSS structure. PRSS structure ensures an uninterrupted current summing in a capacitor and eliminating the interference. Meanwhile, the PSS structure with switches in the path of current introduces a potential interference, and we can counterbalance it with a larger capacitor. Also, about the switching errors, the PRSS structure has a unique characteristic, which it continues to provide currents for a specific time duration, even the source switch is off. This phenomenon is because of the voltage drain source of the transistor. It's implementing the current source remains high. And also about the PSS structure, we have a dynamic and switching errors because of the charge injection from the on or off the switch. First, in one multiplayer structure, we check the output current, we analyze it. For example, in 1.8 voltage, the total current is equal to 300 nanoamperes. So we have this value, the maximum value, and we check it, we analyze it with other configuration, single switch, multiple switch at one in a PSS structure, PRSS structure, and we obtain that single switch PRSS at 1.8 and 3.3 voltage has a better value. Then we have the graph of the voltage over time at 1.8 and 3.3 with the maximum input, which is in the 3.3 we have a T-read of 600 nanosecond, which is the maximum values of T-read. the maximum inputs. And also in 1.8, we have a 300 nanosecond. And our circuit is start with a delay of 50 nanosecond, and we have the positive and negative graphs and slopes, which are related to the positive and negative bits, and also it indicates, reflects the increase or a decrease of voltage based on the current flow. Okay, by computing different structures in both diagrams, we achieved that, reveals that the single switch structure has a better, closer value to the ideal, to the maximum value, and emphasizing its superior behavior performance and also minimal error. In this slide, we analyze the 3x3 multiplayer circuit with maximum input values. All multiplayers has the input values of 15, representing the highest time value, and the 3x3 matrix kernel has values of 15 for positive and negative bits. The output voltage graph at 1.8 voltage reveals that the single switch again structure exhibited the best response comparing to the other configuration. And if you can see here, we have a small slope voltage differences. That means because of the parasitic capacitance and also because of the static errors. Here we have this simulation provides us a more realistic demonstration of a system performance in a 3x3 multiplayer. Here we have, for example, the input. We have this inner product between the input and with the vertical edge detector kernel, and we can see here, instead of having one input, we have 9 different inputs, as we call it, as denoted as T-read, 9 T-read. In the graph of the output voltage over time, with the realistic values, actual values, instead of having maximum values, here as a one single switch, it reveals that this architecture has the best value, closer value to the maximum value. And the final value of calculated through this schematic, this circuit, has a value of 939 millivolt, which is close to the ideal maximum value of 941. Now, in summary, we compared current time multiplication architectures in CNN accelerators. We configure, and the configuration of a current source switching affects the performance, and we investigated parasitic capacitance in both structures, PRSS and PSS. At the end, single switch offers best results, and PRSS architecture shows us accuracy. And for the future work, we develop a complex system with multiple kernel patches, and we are integrating the best candidate into the vision sensor within pixel processing capacity, and then we evaluate power consumption and processing speed. Thank you everyone for your attention.
Thank you very much. You had a very nice presentation. Are there any questions in here? Yep.
Yeah.
I've got some curiosity. So, the conclusion is that it is better to have, let's say, the switch next to the power supply.
Mm-hmm.
Right. Do you have any conceptual reason for that?
In a conclusion,
I mean, from the theory point of view, from the circuit theory point of view, what do you think? Why is that?
The circuit is, what do you?
I've seen that the option with the switch next to the power supply is more accurate than the option with the switch, further away from the power supply. My question is, what do you think? This is, is there any reason for that?
You mean between these two structures? You mean that the PSS structure has better values?
Yeah, the PSS structures.
Yeah, position switches after
the other way around.
Yeah.
The PRSS structure is better than the PSS structure. So
about the parasitic capacitance, yeah, it's better. And at the end, about the because it's reduces a little the impact of parasitic capacitance. And also we have the error voltages that is better than the PSS structure.
Could it be because you have like fixed voltage and you have, let's say, a low impedance, so able to, let's say, to accept any charge at some point in the coil. Now, my second question is about so positive, the positive contributions are provided as errors than negative contributions, as far as I have understood from your slides and from your talk. So the question again is why? What do you think?
Positive contributions, which slide do you mean?
Well, I don't know exactly what this slide, but in one of the tables you showed there was like 0.65% for positive.
Here.
I mean, the error for positive. This one is okay. Doesn't matter.
Yeah.
So, yeah.
Yeah.
Understood positive errors to best.
I mean here maybe. No. Here I think the positive. No, the negative has a better error, and positive it doesn't have. Because of the PMOS transistors, it has a problem. If I want to, for example, in a PRSS structure, I try to increase the width and length of the work on the size of the transistor to make it better. But the thing is, we cannot make it so much big, more than 1 micron. So we increase it until to the 1 micron. But if we want to increase it more, yeah, at the end we have, for example, the error voltage decrease. But the thing is here, for example, in this slope, we have a bigger slope, like, I don't know what's its name. It's the deviation between the difference in voltage. So it's become so big if I increase the size of the transistor. So because of that, I just increase it until 1 micron to have the better value in error. Yeah, and also about the PSS structure, I tried to make it better and working on the switches. I had one PDF, but I think I don't have it here. But I check all of them. I check every transistors in a schematic, but I couldn't increase them more than the minimum, because in the minimum values, the minimum size of the transistors, it works better. I check all of them. But later I have to work on it, because for the next part I have to optimize it.
Well, the thing is that my view is that when you put many things together, maybe some errors compensate for others, in the sense that it seems that deviation from ideality, it's like, it could be a non-linearity, but it also comprises a linearity part, like an offset. My point is, when you have a 3D filter, which is one of the next steps you will do next. So the thing is that when you put together all those 2D filters to make up a 3D filter, my view is that maybe the error is not as important. I mean, not, let's say it simply. So the thing is that,
yeah, in a single multiply, you mean that we have better.
The two-dimensional filters don't contribute. I mean, it's not like an addition of all of them. Yes, when you have the doctoral.
Thank you for your opinion.
More questions here? Also for the people online, if you have any question, you can write it in the chat or just talk. Well, I have a just very probably a stupid question, and I think you have already somehow answered to this. I wonder, because I'm not an expert at all, how do you try all these different structure or architecture? So it's something that is in simulations, or do you
In
actually?
simulation, for example, our postdoc, yeah, the schematic, but we one of our postdoc, he designed the PSS structure, but in 1.8 voltage, and then we tried to optimize it and we changed it so to minimize the interference and other things. So, but all of them, yeah, in a simulation cadence.
Mm-hmm. But then you, at some point, or someone actually implements it and validates all your experiments.
Okay. We have to design chip, maybe.
I don't know. Okay, thanks. No more questions, I assume. Okay, so thank you very much again for the presentation. It was very nice. And I think we can go.
Thank you.